Alright, this may be nothing, but we'll try. So, context. I am generating a bytecode. It's not really bytecode, an instruction style IR, like an SSA style IR, and I'm just cranking through instruction types or node types I haven't done yet. So right now I'm drawing up 3 types of like field access. I have 3 instructions that count as a field access. There's getting an element of an array, getting the payload of an enum, or an ADT, or some type, and also just getting a struct field, and they all work the same way. And we're pulling it out into a function. So let make copy. This is the code that has ended up being the same. So this would be access kind, reference through, okay, stored, right. I don't think that can fail. Load or copy, it cannot. Okay, that's fine. Right, test, yes. Test. So this is where we're meant to put the result of the operation, if relevant. This just, it's like an optimization that we do in pre rather than in post, where if we're running an instruction and we know the result needs to get stored to a given location, we just go ahead and tell the thing that's generating it, just in case that makes it more efficient. Some operations it doesn't help at all, like this one. It kind of can help. Some operations it doesn't help at all because they're doing something where it doesn't matter where the result needs to go, but some it really helps. We just emit a lot fewer instructions. So destination, and then we need the field pointer. So we're calling this a field access. They're all field accesses. And we'll call that the field pointer then. And that's actually just an instruction, which is of some storage type that holds the address of the field. So the result of a gep, basically. The result of some get offset call. Okay. And we need a result type. And that's what we need. And yes. So 3 access kinds. Reference through means the original thing is a pointer, and we want a pointer to the element. So this is like I have a pointer to an array, I have a pointer to a struct, and I want a pointer to its first field. Value to value, this is like I have a value struct and I want its first field obviously as a value. I couldn't even get its an address of its field if I don't even have a place to begin with. And dereference is if I have, you probably guessed it, an address of a struct or an array, and what I want is to dereference. I want to get a particular member of it, so maybe the first field or maybe the 4th element, but then I want not a pointer to that element, I want it dereferenced. Those are the 3 types of access. And if reference through is used, then we're just meant to produce the address. So we're kind of done. We make sure to store it in destination if we were given a destination to put our output, and if not, then we just return field pointer. And that makes this whole operation a no-op if it's referenced through and there's no destination, which makes sense. And then this is the tricky one. So we know we're producing a value here, and it's either a dereference or a value to value. So we perform a loader copy, which kind of just says, hey, if there's a destination, we have a source pointer, and if there's a destination, then we have a destination pointer. So it doesn't make sense to do a load and then a store. It actually makes sense to make use of a copy instruction. So that's what this is going to do. If dest is sum, then it's going to do a copy of this type. And what does copy do? Well, copy says if the type is an aggregate, then do a mem copy. Otherwise, well, I guess copy does a mem copy regardless. It's more like load. Load kind of does different things. If the type is an aggregate, then it does a mem copy. Otherwise, it just straight up does a load. So let's jump into it. But the point is that we need to make a copy if this is a dereferencing operation semantically. Because the whole point of dereferencing is I now have a value that is stable, you know, irrespective of what happens to the pointer I got it from, right? So that's make copy, and this is really simple. You know, if there's destination, we're going to do the copy like I said, and then load value is interesting, where you know, our make copy became copy aggregates, or copy aggregates became make copy here. And it only matters if the kind is an aggregate and we're making a copy. Then we get the layout and we produce copy instruction. Otherwise, we can just point to the pointer as it was. And if it's not an aggregate, then we're just doing a load. So that is all of it. And to search for the 3 call sites here, I'm actually going to search for let make copy, and there should be 4 of them. There are. This is my first one. Let's look. It is the exact same. So now this is just going to be build field access. B field access dot access kind dest field pointer and field access dot result type result, and we'll just go ahead and do that. And that's a really smooth factoring. I'm not normally too gung-ho about factoring this type of thing, but this is representing the exact same logic. And it is something that I could see changing, so I think it definitely makes sense here. If only just to test my theory that it is the same. Field access for an array get element, and this is array get dot access kind. We have a destination, we have an element pointer, and we have a result type ID, which is array get dot result type. Why do we need a result type? Well, the result type might be a pointer to whatever type of element this array holds, or it might be the element type itself, right? But result, and that's fine. You out. The sun is beating down on me, so I don't have much longer. We don't even have that. Going to go array offset. We'll just go array t for sure. BC type is actually, doesn't have to be. We could go all the way. We could at least say it's a BC ag. Interesting. All we actually need is the element type. And that's going to be simpler anyway, and it has to be a value. Yeah, I guess the value could be an aggregate, but we're not going to worry about that. Base, and we'll go ahead and say element index. Okay, and that's our array offset instruction. So of course we need to implement that. That does always produce a pointer. Array offset is going to be element t, array dot. Hopefully it does. Okay, element type. We don't have it. And the index, element index, dot index. All right. Let index. I forgot this has 2 none. Index. This has 2 arguments basically. Yeah, that's neat. Element type, and yeah, that's not a constant. Wait. Is this right? Yeah. Yeah, it's a runtime thing. Obviously. Yeah. Alright. Anything field base? Yeah, that's very true. Okay. Come back to that. And let's go to struct offset. This is checking for errors. Base. I'm not really sure what to check for. The storage, that'd be an aggregate. Which is right. Okay. We could, yeah. I'm okay with this. Oh. It actually needs to be a very specific type of value. We'll let it slide. I mean, technically I need to check all the way that it's a U word, but then I'm like, at that point I feel like I'm kind of just type checking that we generated correct code, which is not the point. Alright, offset, index, type, it's not word, sure, let's just do that. Checking this stuff is always worth it because you generate bad IR and it's just really nice to not debug what happened to a running program, but instead just get alerted to it. Type equals k1 types get array get array type as array. Right. Let element C. We gotta compile it. This is like a bytecode type. That's the AST type. We need the bytecode type. Element type. Yeah. Needs to be a value type. Oh, we don't even need. Oh. Okay, I guess I could go and get it from in here, because when we compile an array type. Sorry, when we compile an array type, we get an ag, right? And that's the element type. We shouldn't call it T. We should call it element T. So let me do this instead. Because I've already done this work, and it's in here. This is going to be expect ag. Let ints kind value c type ag c ag array. Element T. equal else. Copilot, help me out. Return array element on array. Close enough. Close enough. And that gives me element T just once. Element T will be bcmm get element T, because that's a handle. All right, and we did it. And now we just need display. Element T, element index. Right, W array offset. V. Yeah. Let's do the type. So it's going to be array offset U8, and then V array offset U8 at V of the index. V, bear with me. We need the base. Base, right. That's what I was missing. Base and element index. And what's the pointer? Okay, that's it. So simple.k1. Let's, whoops, I don't need any of this. Let's not compile any of that. Let's do let r equals 1, 2, 3, and let's make sure this is an array of iWord. Should be an array of 3 iWords. If I make it 4, it won't type check. Let's go ahead and do that while we check that we are, in fact, we are not currently compiling bytecode, but now we are. And this will make us an array on the stack, on the old stack of Rooney, and we have some code here. And this is what we generated. Alloca, PTR. Okay. Alloca. Okay, space for 3 iWords. And then we store that space for 3 iWords into v3 in case we ever need to reassign this variable. So this is the variable. This is the value. And then we call zeroed, which is a built-in. Neat. That's interesting. Oh yeah, I do. I guess that's the constructor I use instead of uninit. It should probably be uninit. Anyway, then okay. So we call this, which gives us a zeroed array as a value. I haven't done like struct return stuff yet. All right, and then we copy that into v4. Which is where our variable actually lives. So now we're zeroed. And now we're going to load pointer from v3, which is where the base of our array lives. we have the index and the value, and then we're going to call set. Okay, I didn't even... The instruction that we actually wrote is array get. So let's compile that. r.getZero. Wow. It's like a lot of instructions. Because we have bounds checking. Is that written in user space? This array? No. That's just what I generate. This is our crash with a string. I just want to see. All right, here we go. Array offset I word v2. Yep. v2, v29. Load I word from v30. Go to b6. So our value's in 31. It's probably never going to be used again. Okay. Well, I'm relatively satisfied with that. I think we compiled array get element. I need to test the other two access kinds and figure out what's going on with that. What this literal construction desugars to. But yeah, I think that'll be it for now. Thanks for watching.